All right, this is just a little, you know, whatever. Our philosophy is that, we're working at multi-scale. We work subjectively and objectively. We want to iterate through. We believe that working in this nonlinear way makes things more affordable and faster to the table by building tools that support the design concepts. And I'll show you later how we can make real-time adjustments very late in the game with no loss of with no increase in cost. In fact, sometimes you'll drop money right at the last minute. So I can show you that. We, for example, as the bridge is shown with its 3 legs, we had during the slab, while they were casting the slab, they hit something that, a root of a tree that they wanted to preserve. So we ended up just opting out of one of the legs and readjusted the shell very late in the game. And, it was no big deal. So it's okay. So these are some of the early models. Is this the second or first one?
The first one, yeah.
Yeah, so you can see in here some physical models at 1 inch and some bigger shell models. We are drawing on top of the 2 models on the bottom are made of fiberglass, and they became these additive layers that we would cut away and then add some more to. And we draw on them, shoot pictures, and then paint them over and then redraw on them as part of, parsing the shell into different structural systems. The lower right.
Yeah, can you talk about that one? Yeah, this one's interesting.
Yeah, so we did some PVC bents that we used as a full-scale, real-time adjustable tool that the client could walk through. We could talk about because we had this in-place plane that he could walk across, we could relate the new plan to this thing by saying, oh, this should be broader at this point, or we're going to move this vertice this way. And also talking about the ceiling proportionally, relative to the passage, and the idea of having 1 or 2 people pass at the same time, or do you want to have more or less sculptural opportunities in there? So that was the purpose of that.
Okay.
And next one is a version of the acrylic model that we were looking at, some Photoshop work in the lower right, and some Maya in the middle with just different shell types, that we were looking at. And an early version lower is of the voxel logic with a dynamically relaxed surface that the boys at front did for us.
This guy right here?
Yes. So that comes up. We can show you in a bit about that.
Okay.
So next one. This one represents after our earlier efforts. We had a bunch of contenders, let's call them, shell shapes. And you can also see in this image the grid is representing the original surface. We developed physical models for the original design surface. And then in order to make the shell work as a structural shell, we had front do a dynamic relaxation of a surface to approximate our shell shape. And then, as you see in here, we both compromised. They gave a little, we gave a little, and we ended up with something that was a viable shell shape for self-supporting shell.
So this is a bunch of different models overlaid on top of each other. I'm going to say back what you said to make sure I understand it. So you had let's say from these studies, you developed a surface that was sort of your target, and then you worked with that structural engineer, Front Design, right? Or Front Inc.
Yep.
Front Inc. in New York. You worked with them to sort of apply structural logic to that, and then you guys sort of went back and forth. They sent you a model, you kind of compared it to what you had, you made some adjustments, sent the surface back to them, and you guys kind of went back and forth. Is that kind of right?
Yes, exactly. And this model is, a screen capture of Rhino. Just me looking at the different surfaces. I'm putting some planes in there to cut it up and to kind of analyze it proportionally, and yeah. So then the next version, if you click, that embodies our, some of those efforts, early efforts, and the very specific choices into the profile, the heights of each of those curves, and the wing as it comes out the backside. Each had very significant, jobs to do in the property. So.
Let me just go back one sec here. You made mention of dynamic relaxation, and that was something that the folks at Form Inc. worked with you guys on. Can you talk about what that is and sort of the process that your team went through to do that?
Like Friado or like the Gaudi hanging chain models in Sagrada Familia, the catenary that's formed from suspending a surface or a line is going to give you that optimal structural shape. So what Front did was approximate some holding points, and you can see it had to be faked a little bit to get it to take off from the right point in our specific site, but they simulated enough of the point of departure where we wanted our shell to start so that they could let a surface dynamically relax in their structural analysis software, and then offered us back versions of that relaxation. And so we'd change a few parameters with them, they'd come back with a surface, and then ultimately we ended up saying if we make some what would you call it, concessions with our pristine perfect geometry, we could match better the true structural nature of the shell, right? And so, and the one piece down lower, right where you just drew the intersection there, that wing has always been, it had to be considered as a clip-on tie, as I would call it. It's not a part of the structural shape, and so there are moments where trying to decouple the two buildings that we had to make some accommodations, and you can actually see them in the later views of the model where there is a structural frame that rides on the snoot down there. So.
I see. So to say this back to you, so you sort of had a connection point over here along the building. You had these three structural connections where the feet touch the ground, and then you had this connection point here along the building, and as you said, this surface here was sort of independent. And so essentially the dynamic relaxation was putting a surface that was connected to those points and almost turning it upside down, like you said, and use those classic examples, I guess. And then that kind of developed some geometry, but then it probably also developed, some idea about the depth of the structure at these various points and so forth. Is that fair?
We had just the specific locations on the property would have given us some limits to the thicknesses of things. Say there's a window above, on the floor above, so the thickness of the shell at the house had a limit. But there was more specific, as far as the shell shape was, we called that our top of structural voxel, so TSV is what we were labeling it, and that everything worked down from there. So the height of that was just related to leg choice at that point. And early models with the structural draping, they didn't have, you'll see images of them, they didn't even necessarily incorporate the legs at their fullest length. So